We've now seen the ordinary least squares solution and the total least squares solution, both of them in regular and weighted forms, in fading memory forms even. And we have a nice closed form ordinary least squares and not so nice not closed form total least squares solution. And I keep on saying that the total least squares solution is better, but better in what sense? Would like to be able to have a more, rather than waving hands and arguing that something is just obviously better, would like to have a way of measuring if something is better or not. So here in this section we look at an idea of goodness of the model fit. I'm going to come up with a number between 0 and 1 that's based on the measured data and the model fit, and allows us to say in real time as we're operating, is this a good fit or not? And that could be a value. And we also in this section are going to investigate the confidence intervals on the Q hat estimate that we have, some error bounds. And then after that we're going to go on to some further sections which will give us computable approximations to the weighted total least squares solution that will also be quite good. In the derivations we've done so far, we've assumed that the measurement errors delta x and delta y are zero mean, and that is evidenced at least a little bit in the idea that we're treating a positive error and a negative error in the same way. We're simply squaring the errors. But we didn't really take into consideration the assumption that we had Gaussian errors. But that's what we're going to do now. We're going to say the errors are zero mean, they're uncorrelated, and they're Gaussian, allowing us to use some math from probability theory to evaluate the goodness of the model fit. So if I do have these assumptions true, they're uncorrelated, zero mean, Gaussian, then these metric functions that we've defined turn out to be chi-squared random variables. The weighted least squares solution is chi-squared with n-1 degrees of freedom. We've used n data points, or we have n data points to begin with, but 1 degree of freedom is lost when we fit this Q hat. Now, this degrees of freedom is almost like how many equations do I have to fit unknowns, and I have n equations, if you will, and 1 unknown, so I've now got n-1 possible equations. I could consider fitting n-1 other unknowns at most. That's what we mean by the degrees of freedom. The weighted total least squares is a chi-squared random variable with 2 n-1 degrees of freedom. Here we have n data points xi and n additional data points yi, the way we're treating this, that are random. Here the yi are random, but xi is not random, so that's why it's not included. But in the weighted total least squares, they're both random, so I've got 2n random data points, and I lose 1 degree of freedom when I'm fitting Q hat also. Since I know the distribution, chi-squared with so many degrees of freedom, I know that, I can determine using the optimized values of the metric function whether the model fit is reliable or not. So is the linear fit that we have come up with a good fit to the data? And if the slope, the Q hat slope to this linear fit is a good estimate of the total capacity. What does this mean? It means that we're actually going to not only compute Q hat every time interval, we're also going to compute the cost function. And this is a summation, so I can recursively compute it in all cases by adding the new cost. Actually, I don't know if that's true. I'd have to think about that because the Q hat changes. As I change Q hat, that changes the old cost. But in any case, I can at least compute it if I have the data. I compute this chi-squared value, and then I want to see, is this chi-squared value a likely chi-squared value? If it's unlikely, then that means that my model is probably not very good. But if it's likely, that means my model is probably good. So we have to, when I'm looking at likelihood of a random variable, a chi-squared random variable has some kind of shape. It's usually a little distorted. It's not Gaussian. It's usually kind of more like that. And we're trying to say for a certain specific value, shading this curve. So chi-squared, if it's big, that's bad. If it's low, that's good. We know that. So we compute something, an incomplete gamma function from the chi-squared distribution, which is an integral of the distribution. It's defined as the probability that the observed chi-squared should be less than some value for the number of degrees of freedom that we have. So integrating over that and then comparing the value that we have to this cumulative distribution to see if it makes sense or not. The complement to this p function, and p is a standard notation for this incomplete gamma function, and the complement q equals 1 minus p is also standard notation, and I use this here. In our context, it might be confusing because q is capacity, the number q is capacity, the number q hat is an estimate of capacity. This is neither. This is a function q. So observing that it's a function might help you distinguish between it. It's not either of the first two things. It's a third thing by itself. And it's defined to be 1 minus the incomplete gamma function. It's the probability that the observed chi-squared will exceed the some value in the argument of this function by chance, even for a correct model. So what we're going to have to do a goodness of fit test is to evaluate this complementary incomplete gamma function q, and we look up in our Prob and Stats textbook what that function looks like, and here it is. It's 1 divided by the gamma function evaluated at nu over 2. Nu, here the Greek letter nu, is the number of degrees of freedom. And you say, okay, what's the incomplete gamma function? You look that up and you say, oh darn, it's itself an integral. It's not very pleasant looking to be able to compute that. And not only do I have that gamma function in the denominator, I have an integral. So I have to be able to compute an integral from the chi-squared over 2 all the way up to infinity of e to the minus t, t to the nu over 2 minus 1. Wow, that looks awful. In fact, there are well-known, well-established methods for computing this function. They're built into many engineering analysis programs. For example, the MATLAB Probability and Stats Toolbox has it built in. And if you look on the internets, you can find C language code for computing this function also. So yes, it doesn't look pretty, but it's completely doable. There is no impediment to doing it. You don't have to make up your own way to do it either. So what are we going to do? What we're going to do is we'll compute our chi-squared value based on our estimate of q hat and our data, and we'll stick our estimate in here and evaluate this function. We know the number of degrees of freedom. It's either n minus 1 or 2n minus 1 depending on the method, and we'll get a number, and this number is going to be between 0 and 1. If the number is small, close to 0, then one of maybe 3 things has happened. So either the model is wrong. This is not a good model for the data, which either means that it's not a straight line or that my q hat is bad. Then that means that I need to just reject my q hat estimate. I can't trust it. That's one possibility. Or the other possibility is that the variances that I've used in my computations are actually not well known. And so my q hat may in fact be good, my model may be good, but I just don't know that it's good based on my variances which go into computing this cost function. So my cost itself may be bad, even though the model on the Q hat may be good. Or the variances may actually turn out not to be Gaussian. Now this is usually true. It's rare. I mean, it's probably never true that we have an exact Gaussian, but the literature seems to indicate that even if I don't have Gaussian errors, as long as they're zero mean and uncorrelated, that's probably not a big deal. We just need to be willing then to accept fairly low values of Q as a good fit. You think of, oh, okay, near 1 equals good, and near 0 equals bad. Well, what does near mean? What's my threshold? And you might say, oh, my threshold is 50%. I want it to at least be half likely to be good. Or you might be a purist and say, oh, my threshold is 99%. I want to be really sure that it's good. It turns out that in practice, as long as you're above something like 0.001, you're going to be good. If you have a bad model, the Q value obtained from this complementary incomplete gamma function, it goes to almost exactly 0. So if it's bad, it's really bad, is what the answer is going to turn out to say. So that's not unusual. So maybe you would be concerned with that level of acceptance, but do some experiments. We're going to do a homework project where you're going to be computing this and looking at it, and you're going to see that after very few updates, maybe 10, 15 updates to your capacity estimate, it's either going to converge almost exactly to 1 or almost exactly to 0. This turns out to be a pretty binary thing. That's what I say here. So when the hypothesized model is equal to the true model, even when Q hat is not precisely equal to Q, this value of Q tends to be very close to unity. If the hypothesized model is not a good model, then we become very small, very close to 0. And we will use this later on in an example to show that the weighted least squares model is not a good approach to total capacity estimation, but weighted total least squares is much, much better. So keep that in mind. This is how we're going to be able to more numerically show and quantify the fact that the total least squares method is better than the ordinary least squares method. We also want to talk about confidence limits on the estimate that we come up with. One really nice feature of the Kalman filter, and one reason we might want to use it even though it turns out it's suboptimal for capacity estimation, one really nice feature is that it gives you not only the estimate of some quantity, but it gives you the error bounds on that estimate. And that allows us to use to understand, how much confidence to put in that estimate when we use it later on. If I have my estimate of total capacity, I'm going to use it to compute the energy of my battery pack. Well, if I have a capacity estimate that's 10 amp hours plus or minus 1 amp hour, that means something substantially different from an estimate that's 10 amp hours plus or minus 5 amp hours. And hopefully would be even closer than plus minus 1. So having a confidence estimate that's built into the algorithm, that's dynamic, it updates as you collect more data, is really, really valuable. And we have that for the Kalman filter, and so far we don't have that for this method here. And that's what we're going to develop in this section. We'll develop a method that allows us to compute this confidence bounds on Q hat. We would like to estimate the variance of the total capacity estimate, and then that allows us to say things like, with very high certainty, the true capacity is between Q hat minus 3 sigma Q hat and Q hat plus 3 sigma Q hat. That's what we mean by the error bounds. And of course 3 sigma is 99.7% if everything is Gaussian and whatnot, but 3 is a little bit arbitrary. You choose whatever number of standard deviations you think is best for your application. To get these confidence limits, we're going to have to think about our least squares type optimization problem in a different way. Least squares, because we have squared all of the errors and summed them up, and then we want the least value, the smallest value of that. And we're going to rethink this as a maximum likelihood optimization problem. Maximum likelihood looks at a probability density function and tries to find the input to that density function that gives the maximum point, the maximum likelihood. If we assume that all of the errors are Gaussian, it turns out that we can actually recast like this in a very straightforward way. Let's look at how to do this. We form a vector y that has all of the elements yi and a vector x that has all of the elements xi. We've done that before. That's nothing new. What's new now is a diagonal matrix sigma y that has on its diagonal all of the variances, the sigma squared yi. Then that allows us to write our weighted least squares cost function, which, if you remember, was the sum of yi minus q hat xi squared over sigma yi squared. I could think of that as, okay, that's the sum of yi minus q hat xi times 1 over sigma yi squared times yi minus q hat xi. So I've broken the squared up into two parts, and that summation then can be written in vector form as the vector yi minus q hat vector xi, not I, sorry, because the vectors don't have I, it's just y minus qx, and then this sigma is going to be this sigma y inverse, and then y minus q hat x transpose. We have to transpose to get this, actually transpose this side to get it in the right form. So these two cost functions are the same, and minimizing this is the same as minimizing this. Let's look at this maximum likelihood for corresponding to the weighted least squares solution. There's a number out front of the exponential. Let's ignore that for a second. I've got an exponential. I've got this minus a half, which is different, but all of this is the same as that. If I want to minimize that thing, this thing, that means I want to minimize this thing. If I divide it by 2, it really doesn't have any impact on minimizing it. If I multiply it by the minus 1, that would be, I want to maximize, really. So I want to maximize that thing because of the minus sign. exp is a one-to-one function, so I want to maximize this exponential term. And notice that this is just a constant. N is a constant, 2 pi is a constant, the determinant of the sigma is a constant, so that's just a number that makes this PDF turn out to be a Gaussian PDF and integrate to 1. Bottom line, minimizing the least squares cost function is the same as maximizing this likelihood function. Similarly, this is for the least squares solution, or ordinary least squares solution, or weighted least squares solution. We could make a similar analysis for the total least squares solution. We take the y variables and the x variables, and we stick them into a vector y and x on top of each other, and we call that D. And we have a D hat vector which has all of the capital Y and X stuff concatenated together. And we have a sigma D matrix which has diagonal elements sigma y squared followed by sigma x squared on the diagonal. Then going through the same kind of steps, we say that minimizing the weighted total least squares solution is equivalent to maximizing this Gaussian PDF. That should be bold-faced there. So in both cases, we can show that the minimizing least squares is the same as maximizing this likelihood function. Now, why is that critical? Well, in maximum likelihood theory, there's something known as the Cramer-Rao theorem. The Cramer-Rao theorem allows us to establish the confidence intervals on Q hat. And it puts a lower bound on the variance of Q hat. So it says, I'm going to give you a number, and that number is less than the variance of Q hat. It's kind of the most optimistic guess as to what the variance of Q hat is for you to do error bounds. So your error bounds are actually going to be worse than the number that I give you, but most of the time it's not going to be a lot worse. It's a tight lower bound. It's not a loose lower bound. The number that it gives us is based on the inverse of the second derivative of the guts, the argument of the exponential function. So I take, the exponential function, what is that? Well, it's minus a half times the cost functions that we had already. So taking the derivative and the inverse and the negative, so the negative a half becomes positive 2, and we get the variance of the estimate for total least squared solution is at least as big as 2 times the Hessian of that cost function inverse. And the variance of the total least squares is, again, at least 2 times the Hessian of that cost function inverse. So again, we see this Hessian thing come up. It's not something that comes up all that often in the kinds of courses that I teach, but here in just the matter of a few pages, we've seen it twice. One of them was for a Newton-Raphson iteration for optimizing the weighted total least squares cost function, and here for evaluating the Cramer-Rao theorem to give us confidence intervals on our capacity. So if I have to find the Hessian anyway, then I might as well use it for as much as possible, in this case to give me these error bounds. We already derived what the Hessian was for the weighted total least squares. You can go back a few pages and see it. It's a summation. It's a little bit ugly, but it's completely computable, not too hard. We can do that. We did not, by the way, find the Hessian yet for the weighted least squares solution. We can do that. We take the second partial derivative of the cost function with respect to Q squared, and it gives us this, and for the fading memory weighted least squares solution, it gives us this, and say, wait a minute, this looks pretty familiar. We already defined this to be something that we called C1, so the Hessian is simply 2 times C1. And we already defined this here. We call that C1 tilde. So the Hessian is simply 2 times C1 tilde. Now that you see that, even though you could say, this Hessian, it looks pretty grim, I don't know if I want to do that every time through my iteration simply to find an error bound. Now you see, okay, I can relax. This is based on something I've already computed. I've computed these C1 values, whichever way I'm doing this, fading memory or not. I just have to take that and multiply by 2. And by the way, that 2 ends up being in the, this is inverse. So for this, it's going to be sigma q hat squared is bigger than equal to 1 over C1n or C1 tilde n. The 2's are going to cancel out. This is not hard to compute. It's trivial to compute, and now we have error bounds on Q in a very easy way. So in this section, we've looked at two important concepts. One of them is, how do I know if this model even fits the data, and I can compute that in real time and have a good idea if I can trust my capacity estimate or not in that sense. And then what are the error bounds on capacity? If I determine that the model is okay, what are the error bounds on capacity? And we can compute those as well. But we are left with the problem that the weighted total least squares solution is not easily computable. We would like to have a way of simplifying that solution. And in one situation, with one set of assumptions, we'll find that we can find a simplified solution with a closed form and all kinds of nice properties. That's what we're going to look at next, and then we're going to find an approximate solution for the most general case too.